The focus of this lesson is on solving a polynomial inequality using test points. And the first step is to make sure one side of your inequality is 0. In other words, all the terms need to be moved to the other side of the inequality. And so that step is already done for us. So then we would move on to our factoring techniques to factor that non-zero side. And we can see, since we have like 4 terms here and we're degree 3, that grouping is probably a good method for factoring. So I'm going to start off by grouping our first 2 terms together, and then I'll group our second 2 terms together. And so for our first 2 terms, the GCF, or greatest common factor, is x to the second. So if you divide out x to the second from those first 2 terms, you're left with x to the first minus 1. And then for the second 2 terms, the GCF, or greatest common factor, is positive 3. And if you divide that out or factor that out from both of those terms, you're left with x minus 1. So notice in both cases you're left with x minus 1, and so you grouped in a way that is useful to you because that is the goal, to get those to be the same. And so then you would go ahead and factor out that common factor of x minus 1 from both of those pieces, and when you factor that out, you're left with x squared from that first piece and plus 3 from the second piece. And so this gets you the factorization of your polynomial inequality. And then what the next step is to determine your boundary points, and you get that by setting each of your factors equal to 0. Now our second factor here of x squared plus 3, if we set it equal to 0 and we use a quadratic formula on it, we'll see that it produces imaginary solutions, and we're only concerned about real solutions and real boundary points, so it's kind of irrelevant as far as boundary points are concerned. So the only factor we're going to look at is x minus 1 and set that equal to 0. And when we solve for x, we'll add 1 to both sides, and we're left with x as a positive 1. And so that's our only boundary point that we're going to use or need for this problem. So I'm going to draw that on a number line. And you could see basically that if I split our graph right there, we're left with 2 intervals. So from negative infinity to 1 and from 1 to infinity. And as far as those intervals are concerned, 1 is a value in which our polynomial equals 0, and that will be part of our solution. So no matter what, at the end of the day, I know 1 is part of my solution to my problem. So hence why I have brackets to designate inclusive on each of my intervals, because I know it'll be included in the solution. So then what I would do from there is I would pick a test point on both pieces. So to the left of 1, you could pick any value to the left of 1, so I'm just going to pick 0. And what I would do with that value is I'd plug it into the factorization polynomial that I had. And when I plug it in, all I'm concerned about is the signs I get for each of the factors. So if I plug in 0 into x minus 1, I get 0 minus 1, which is negative. If I put in 0 to the x squared plus 3 piece, I get 0 squared plus 3, which is positive. So my sign overall is negative times a positive, which is negative. And then I would do the same thing for my second inequality, so basically to the right of that 1 value. So I might pick a test point of 2, and I'd plug that into my factorization. 2 minus 1 would give me a positive, and 2 squared plus 3 would also give me positive. Positive times a positive is positive overall. And then as far as our solutions are concerned, we are looking for the values in which we are greater than or equal to 0. So that means where we're positive or equal to 0. So we can see this is where we're positive overall. So, and then we're equal to 0 at that 1. So my solution, so this is where we're positive. My solution is from 1 to infinity. So every value within that interval is a solution to my polynomial inequality.